I work for Valve on RADV, and welcome to my presentation about RADV's ray tracing. So we're gonna start right off, if the slides can actually move. Like, do I need to point it somewhere? There we go. So we're gonna start off by just recapping the Vock ray tracing API from an application perspective and how it uses it to actually do ray tracing like in your app. And after that, we're gonna look at how we implement these same APIs in RADV. And in both cases, we're just gonna start with acceleration structures and then move on to ray tracing pipelines. So first of all, we're gonna look at the acceleration structures. And they're basically the main scene container that if you want to trace some rays across a scene, you'll put your scene into that acceleration structure and give it to the driver and tell it to trace some rays. So this whole structure is, of course, dependent on which exact ray acceleration hardware you use. So it's completely opaque from the app's point of view. It doesn't actually know what binary data is encoded inside that acceleration structure. And to actually construct these structures from your average triangle mesh or whatever, you just kind of give all your triangles to the driver and just tell it to, hey, please build this acceleration structure for me. There's also some other primitive types aside from just triangles. You have ABB primitives, which, for example, you can use for procedural geometry. If you have your geometry that's not defined by some amount of triangles, but rather by some equation, you can put in the ABB of this primitive that's going to be defined by the equation, and then you're going to give the driver some piece of code that will calculate whether a given ray intersects with that geometry or not, and that way you can kind of have any sort of intersection function or geometry that you actually want with this ray tracing. Another primitive type is an instance of another BVH. So if you want to have like 2,000 trees in a scene, you don't need to actually build 2,000 different acceleration structures for these trees. You can just build one and copy-paste it into another acceleration structure. And Vulkan sort of enforces this behavior between instancing other BVHs in that it has a top-level acceleration structure where there can only be instances of other BVHs, and these instances can only be bottom-level acceleration structures, and those themselves can only be composed of these triangles or ABBs. So in the end, you always have this top-level acceleration structure, which will refer to some bottom-level acceleration structures containing some triangles. Now, with that in mind, let's trace some rays. We have the ray tracing pipelines, a special type of pipeline specialized for that. So usually you'd have your graphics pipelines for performing rasterization or compute pipelines for performing compute operations. And ray tracing is basically the same thing, but just for ray tracing applications. With that, there comes a new set of shader stages. So before you'd have like vertex shaders, fragment shaders, and compute shaders, and so on. And ray tracing introduces a whole bunch of new shader stages called ray generation, any hit, intersection, closest hit, miss, and callable. And the control flow between these stages is sort of complex. So in a ray tracing pipeline, in a rasterization pipeline, you just go from vertex shader straight to tessellation, geometry, and fragment, and so on. In the ray tracing pipeline, this whole thing is a bit more complex, but you do start with a specific shader, which is called the ray generation shader. That's basically used to set up some cameras, determine from where the ray will start and the direction in which the ray will be traced. And then you'll end up calling trace ray. That jumps execution to a ray traversal function, which is defined inside the driver. And that's where the ray hardware will traverse your acceleration structure and try to find intersections with primitives. If you find an intersection with an ABB primitive, you call the intersection shader, which is responsible for determining, with procedural geometry, determining the intersection points of rays for that equation you set as for the procedural geometry. It can, of course, report that hit to the driver, which will then jump execution to the so-called any hit shader, which can then evaluate that hit if it should actually be considered. For example, if you have some geometry that has an alpha texture and you want to do transparency correctly, you would sample that alpha texture in the any hit shader and reject the hit if it, for example, the transparency is 0, because then you didn't actually want that particular location to show up at all. If you have triangles that are hit, then of course the intersection shader doesn't make any sense, so we just jump directly to the any hit shader. And intersection shaders and any hit shaders can both reject hits. In the intersection, that's just not reporting any hit. then execution will just jump back to the rate reversal, where it will try to find more intersections that it can pass to intersection or any hit shaders. If you do find an intersection and the any hit shader confirms it, then you'll end up in the closest hit shader. And of course, if you have multiple hits, then you need to choose one. And the one that is chosen is always the one that's closest to the ray origin. That's where the name closest hit shader comes from. And if you don't have any hits that were accepted, either there were none found in the first place or the any hit shader rejected all of them, then you're going to go to the miss shader, which will then just execute some code that you, example, want to set for sky colors or something. And that's what you, for example, would do in that miss shader. There's also another cool thing about ray tracing pipelines in that you can actually do full recursion. That means you can call the trace ray function from the closest hit and miss shader again, and that will jump back to the ray traversal and do the whole traversal loop with intersection and any hit shaders again, and then call more closest hit shader and so on and so on. But there's always a driver-defined limit. So for example, on RADV, you can't go above 32 levels of this recursion, and there's drivers where you can't even do any recursion at all, so the max recursion level is just 1. Another shader stage I didn't talk about is callable shaders, and they're sort of separate from this whole control flow of the normal ray tracing pipeline, and they can be invoked from any shader that's outside this ray traversal loop. So intersection and any hit shaders can call callables, but ray generation, closest hit, and miss shaders can. Also, callables can themselves recurse again into other callables, so you can call callables from callables and so on. Now, there's all a lot of flexibility, and we have a few other concepts to kind of support that. The first major concept is the shader binding table, where you can have more than one shader for each stage, and to determine which shader is actually called, you store references to these shaders in that shader binding table, and when you call, for example, a closest hit shader, then the driver will look at the closest hit shader binding table to find out which handle of the shader to execute, and then it will jump to the shader that's referenced by that handle. If you're familiar with jump tables, it's basically the same thing, but just on the GPU. And if you have that many shaders, it's also useful to move some common shaders out into a separate compilation if you want to use them in lots of ray tracing pipelines to not have to recompile them again and again for each ray tracing pipeline. And that's what pipeline libraries are there for. You can move these shaders out into a different pipeline library and just reference it from any other ray tracing pipeline that might want to use them. This library concept was later reused for the graphics pipeline library extension, so if you're familiar with that, it's sort of a similar thing, but just for ray tracing pipelines. Now that we've got a rough overview of the API, let's look at how we actually implement this thing, and we'll start with acceleration structures again. So on RADV, acceleration structures are implemented as so-called bounding volume hierarchies, or BVHs, which are basically just a tree structure made from your triangle or whatever mesh that you gave to the driver. So in that tree structure, each leaf node of that tree will be equivalent to one triangle in your mesh if you have a triangle mesh. The parent nodes of these leaf nodes are then so-called internal AABB nodes, which just aggregate multiple of these triangles into one AABB, and that's basically what the nodes represent. And these internal AABB nodes have some other AABB nodes as their parents, so we just aggregate everything into fewer and fewer AABBs as we go up that tree. And when we reach the root node, then we'll have one AABB that basically encompasses the entire scene. And that's useful for ray intersection acceleration because, for example, if you have a ray that just goes way outside the scene, then you can immediately reject that ray because it likely doesn't even hit the root node's AABB, so you can just test against the root node and immediately say, yeah, that ray misses completely, just execute the miss shader. And that also works for like deeper levels where you have like only one child node that actually hits the ray and all other child nodes miss, so you can discard all of those child nodes and only look at like the one child node that actually hits. In AMD hardware, we have a so-called BVH4, which just means that each of these internal nodes has 4 other nodes as its child nodes. And I've actually got some structures that actually represent the ray tracing nodes as they're used in RADV. So for the internal nodes, we refer to each child node as a 32-bit integer pointer, which packs both the ID and type of that node. So we can distinguish whether we are pointing at another internal node or a triangle node or whatever. And this type is packed into the least 3 significant bits, and node offset in that BVH in multiples of 8 is packed into the other bits, which essentially makes the required alignment for these BVH nodes 64 bytes, because the least 6 significant bits are unused. So that's what the 4 other integers at the end of the ABB node are there for, just to have the proper alignment when we have lots of these structures in an array one after each other. For the triangle node, we of course first store each vertex of that triangle to check against. And then we also store some other metadata, like the index of that triangle within the geometry it belongs to, the index of the geometry it belongs to, as well as some other flags for that geometry that influence some things about ray traversal. We also have the ID member, which essentially tells the hardware to reinterpret certain things about that node structure, but we just set it to a hard-coded value for now. Now, building acceleration structures is kind of a multi-step process. We first convert each input primitive to one leaf node, and then we sort all of those leaf nodes, because the app might provide these leaf nodes in some random order, we don't know which, and it's pretty unlikely that that order will be useful at all for BVH building. So we use a concept called Morton codes for sorting. And the cool thing about Morton codes is that they are constructed in such a way that if you have triangles that are close together in space, their Morton codes will also be numerically close. So if you then sort all of your nodes by these Morton codes, you will have nodes that are close together in space also be close together in memory. And that's useful for further BVH building. Then we use some algorithms to construct a binary BVH, and we mostly use the binary BVH at first because all of the research algorithms for BVH building only concern themselves with these binary BVHs. At the last step, we just convert that binary BVH into the BVH4 that's actually used by the hardware. Now, a big disadvantage of having this many steps is that you actually need to synchronize the whole execution in between each step. You can't just start sorting nodes when you don't actually know which nodes you're going to have in the end. So we have to insert pipeline barriers between each of these steps. And if you have lots of tiny acceleration structures that you build one after another, that's going to be terrible for GPU utilization. That's why Vulkan also has a concept of batching multiple acceleration structure builds in one command, and then we can just execute all of these steps in parallel for each of these acceleration structures, which kind of solves that problem. And this batching actually makes a huge difference in practice, because if you don't batch, your thing's going to look like, your GPU utilization graph is going to look like this. And that's basically the worst case you can actually get. Like, you have around 100 milliseconds of frame time, which equates to 10 FPS, and 60 milliseconds of that, so roughly 2/3 of that, is just spent building acceleration structures with really garbage utilization. So it's best to just batch. Now, I'm going to take a quite short look at how we actually implement these binary BVH building algorithms, because we have 2 of them. So the first one is pretty simple. It's the linear BVH algorithm, which is from 2014, and just builds up a radix tree from the generated Morton codes we generated earlier. And the cool thing about this algorithm is it can build up the entire tree completely in parallel, which is great for executing this on a GPU, because you don't need any sort of synchronization in between tree levels or anything. That's why we use it for builds where this whole build process needs to happen really quickly, and we don't actually care that much about how good the BVH is in the end. Like, it's not terrible, but it could also be better. This is, for example, the case for many top-level acceleration structures that just contain all the objects in the scene, because there likely won't be as many objects as there are triangles in the scene, and most of the time the objects move around somehow on each frame, so you need to rebuild that top-level acceleration structure each frame, and having a quicker build algorithm just helps make all these rebuilds faster. The other algorithm we have is parallel locally ordered clustering, or PLOC for short, which is better quality than LBVH, although it's quite a bit slower. This is mostly because it actually needs to synchronize after building each tree level, and we don't know how many tree levels we have to build in advance, so we can't just emit some pipeline barriers and be done with it. We actually need something to trigger a whole GPU-wide synchronization from inside the shader. The original implementation of this algorithm was written in CUDA, which has a special intrinsic for this, so they didn't have that problem. But our build shaders are written in Vulkan GSL, so we have a big problem on our hands. But we solved this by making our own kind of synchronization primitive for this, and that's what I'm going to talk about next. So since our build shaders are written in Vock and GLSL, we don't have many intrinsics we can play with, but we know the target compiler and we know the target hardware, so we can make some extra assumption about this. For example, we can assume certain things about independent forward progress. That is, if we have some invocations that just continuously poll a value in memory and busy wait on that until it changes, that actually won't starve any of the invocations doing actually useful work. So at some point, if the invocations doing useful work aren't starved, that they'll finish and we can exit that busy wait loop and continue on with our work. Another guarantee we can make is about launch ordering. So if we have a compute shader invocation that launches with a certain launch ID, we can assume that invocations with a smaller launch ID have been launched already. So that's basically used in some other places to implement a lighter sync without actually having to synchronize the whole GPU every single time. The thing that we went for the whole GPU synchronization is basically a work stealing queue with unsigned integers as the task IDs, and that's basically just what you refer to for each task. So it has a unique identifier, so you can figure out what to do given that unique task ID. We also needed to have a runtime defined number of tasks to launch before synchronizing, because we also don't know how many nodes there are in each tree level before we actually build the tree level. So we need to know we need to determine how many nodes we have to launch before we actually, just before we launch that shader for building those nodes. So launching new tasks is pretty easy. We just atomic add to some task counter, and that gives us a unique task ID. But actually making sure previous work is finished is a bit more involved. We maintain a finished counter that just keeps track of how many tasks are finished, and we have a maximum task ID. So we keep track of how many of the maximum task ID that needs to finish before we can launch new work. And then we just compare if our current task ID is greater than that. If it is, we need to wait until the task ID gets incremented. And the last invocation to finish its task that would just wait otherwise, that one will update the maximum task ID to launch new waves and free them from this busy wait loop so they can do their work. Now, this was a bit oversimplified. The actual algorithm for this is a tiny bit more complex. But this is pretty much what we use, and it's served us pretty well, actually. We are pretty competitive to the AMD proprietary driver in terms of build times, so this is mostly just what we went with, and it's been doing us pretty good services so far. Now let's talk a bit about how we actually implement the ray tracing pipelines, because that's basically where the second or the biggest changes since XDC 2022 happened. So the hardware actually provides us with some parts that accelerate ray BVH intersection, which is this image BVH intersect ray instructions. And that just calculates the intersection results for a single BVH node. So if you have one internal ABB node that you want to test against, that instruction will go through each of the 4 child nodes, test that against the ABB, and test its ABB against the ray. And then it will give you each of these child nodes that hit the ray is sorted by the intersection distance. So the ABB or the child node that was intersected the closest to the origin will be returned first, and other nodes will be returned later. It has also another mode for triangle intersections where it will return how far the intersection was away from the origin and at which barycentric coordinates inside that triangle the ray actually hit. That's useful for shaders because they do some per vertex parameter interpolation stuff based on that barycentric coordinates. So we also have some new concepts in RDNA 3 that were added there, but RADV doesn't actually use those yet, and I think we're kind of running out of time, so I'm going to skip over those. But that's pretty much all there is for the hardware, and all the rest is implemented in software. So the software implementation has changed quite a bit over the last years. So at XDC 2022, we had basically this kind of implementation where we just inlined everything, the whole ray tracing pipeline, into a single compute shader and refer to all of the shaders by their IDs. So we had like a giant switch case for each of the shaders, and if their ID matched the ID that we wanted to call, we'd execute the code for that shader. And since there's arbitrary recursion and you don't actually know how many shader calls you're going to make, we also had like this while loop, so we continually would call new shaders until the shade ID was set to 0, which would signal that we should exit the shader instead. Now, in XDC 20, nowadays, we have encountered quite a few problems with this. The biggest problem is just that ray tracing pipelines are really big. Like, games create up to 2,000 shaders in a single ray tracing pipeline, and stuffing all that into a single compute shader isn't going to work. We've had shaders that were so big, when we executed some recursive compiler passes for them, we just ran out of stack space and crashed completely. So that wasn't really a sustainable approach for bigger compute and ray tracing shaders. So we changed that up a bit today. And another limitation of that approach was that the whole concept of pipeline libraries, where you just compile your shaders or parts of the ray tracing pipeline beforehand, doesn't really work, because you need all of the shaders inlined into single shaders. So you can't just compile parts of the ray tracing pipeline at one point and other parts at some other points. So nowadays we have two different modes for compilation. The first mode is the monolithic mode, which in many ways is pretty similar to the XDC 2022 mode. But the most stark difference there is that we don't support recursion in this mode. So we can just copy-paste all of the shaders at the sites where they're actually called, instead of having to do this while loop thing. This also allows us to do some constant propagation in some cases. If we, for example, call this trace array function with compile time constant ray flags, any branch that checks for these ray flags can be flattened at compile time, because we already know which code path will be taken. This code path also doesn't support any pipeline libraries, but we might get to that later, depending on how well they'd fare with the added complexity of just much more shaders in the programs that actually use ray tracing pipelines libraries. So the other mode that we have is the separate compilation mode, where we implement these shader calls with an actual indirect jump. And that allows ray tracing shaders to be completely compiled separately, so we can actually use the pipeline library functionality. But this comes at a cost of being pretty complex, and also we can't just inline every single shader. So the intersection and any hit shaders are still inlined into a single big traversal shader that then encompasses pretty much the entire ray traversal loop. And just the shader calls outside of that I marked in green here, are implemented with actual indirect jumps. So the traversal shader looks something like this. We have the main loop that just fetches a node and executes the hardware instruction for it. And if we see that we need to execute any hit or intersection shaders, we just copy-paste them into the traversal loop. And if they reject the hit, then we just continue finding new intersections to test against. And at the end, where we don't have any new intersections anymore, we call either the closest hit or the miss shaders, basically. So there's a few reasons why we didn't separately compile any hit and intersection shaders. The most important reason is that ray traversal has lots of live states. So if you have an any hit shader that rejects some hit, you need to return to the shader at exactly the same point where you left off. And that requires saving lots of variables, and that can get expensive really quick. Also, you call lots of ray tracing shaders in the process of the ray traversal, because you have lots of intersections to process. So this higher overhead of each shader call gets multiplied by just doing much more shader calls to any hit and intersection shaders. So in the end, it was just always net negative on performance. So for implementing indirect jumps, we have the problem that each wavefront that has 32 or more shader invocations can actually only execute one shader at once. So we need to select one of the shaders from each invocation to determine which one to jump to next, and then just mask off all of the invocations that didn't actually want to call that specific shader. The problem with that is that in some cases, you might have some scenario where you have a shader call graph like this, where you diverge at a closest hit and a miss shader, and then reconverge at the ray generation shader. So both invocations that I show here, that will call one will call the closest hit shader, one will call the miss shader, but they're both called the same ray generation shader again. So if you just do the most naive approach of reading the first possible, the first valid shader pointer, you'll have an execution of something like this, where you start at the ray generation shader, of course, jump to the traversal shader, and then diverge at the closest hit and miss shaders. But when you actually execute the next step, then the second invocation will still be stuck at the miss shader, but since the first invocation wants to go to the ray generation shader now, we will first jump to the ray generation shader, where the first invocation will become invalid. Then we'll jump to the miss shader back, and after that we will execute the same ray generation shader again with the second invocation active only. So we can actually do better than that, where we select the shader based on its type, where we prefer, for example, closest hit and miss shaders over traversal shaders and ray generation shaders. And usually if you implement these indirect jumps for shader calls, you don't actually know the type of the shader, you just have some address and you don't know what type of shader there is. But we can actually circumvent that by exploiting the fact that on AMD, instruction always need to be aligned to 4 bytes, so the least 2 significant bits of the instruction pointer are always 0. And there we can pack some shader type information in, and that's where we get the info on which shader to execute from. So if we prefer the closest hit and miss shaders first before executing any ray generation shader, the same loop would look like this. We go to the first traversal shader, go to closest hit and miss shaders, and diverge there. But instead of directly going to the ray generation shader, we execute the miss shader first, and then execute the ray generation shader with both invocations active. So I'm having not much time left, so I'll just go over the ray tracing status now really quickly. We've made lots of progress in compatibility. Like we had these games that worked at XDC 2022, and everything else was basically a gamble. It most likely didn't work, so probably don't even try. But nowadays we have pretty much everything that's out there working. So if you just run a random ray tracing app with RADV, the chances are really high that it works. We have some hangs in The Witcher 3 and Cyberpunk 2077 currently, but that's pretty much all we know of. Of course, if you know of anything else that hangs on RADV, please report an issue and we'll try to look into it. But usually the expectation is that it works. We've also made some great progress in performance. We've gone in this ray tracing reflection sample. We've went from around 1300 FPS to around 1600 FPS. Of course, we have still some optimizations to do before we actually match the AMD proprietary driver here, which currently reaches around 2000 FPS. But with that, let's look at what we actually want to do next for ray tracing. And the most important and obvious bullet point is to make the remaining games work. And the next step is to make them work actually fast. And for that, we have a few ideas. We have lots of flexibility with the indirect jump shader calls, so we could explore some more sophisticated techniques for these shader calls, like shader execution reordering. But on the other hand, we could also look into expanding the monolithic path, which of course has much less shader call overhead, and making that work with pipeline libraries instead. Also, of course, on the roadmap is taking advantage of the RDNA 3 features I skipped over, because RADV doesn't actually use them yet. And on the acceleration structure side, we could either build higher quality BVHs, so we have to execute less traversal iterations, which of course makes the overall thing faster. And the other thing we could look at is acceleration structure updates, where Vulkan has some ways to modify already built acceleration structures without the hassle of having to do all the thing with rebuilding it again. So you just kind of change some small positions about inside the acceleration structure, and that's it. You usually don't have that much time spent in the building there, but RADV actually doesn't implement this update path, so we just always rebuild from scratch, which could be optimized to also update, which would likely reduce the time spent building acceleration structures even more. And of course, lastly, we have tons of micro optimizations everywhere across the stack that we could do to make RADV ray tracing much more than just the world's slowest ray tracer. And that pretty much wraps it up. So thank you for listening. I hope you enjoyed, and I'll be happy to hear any questions. No hands? That obvious?
What kind of work is there left to do for RDNA 3?
So it's basically just implementing the instructions that requires lots of refactoring in the ray traversal loop, where all of the instructions are currently aimed at. Like you have all of the shader instructions pretty much aimed at accelerating ray traversal. So lots of refactoring in that ray traversal shader that we have would be required to make use of these instructions instead of doing what we currently do, which is emulate the corresponding functionality in software. So it's basically just refactoring and then plopping the instruction in.
When you go from binary trees to these BVH4 trees, do you just collapse levels? Is there some cleverness to it?
So basically, the thing with BVHs is you don't actually always have 2 children or 4 children. Like, some of the children can be invalid, and the one non-trivial optimization we do instead of just collapsing is if we have another child that is invalid, we pull up more children from the other side so that the BVH in total gets flatter, and that means less traversal iterations.
So you're rebalancing the tree as well. Cool.
Okay, I think if there are no questions from Matrix or anything, then I suppose thank you for listening.